In our last lecture on pulmonary physiology, we talked about pulmonary ventilation, that is, movement of air into and out of the lungs. But of course, until that air can be exchanged with gas molecules in the blood and ultimately with the tissues, it's rather pointless. So now we're going to be talking about gas exchange and actually what makes that exchange occur. Well, gas exchange is due to diffusion of gases. And diffusion is caused by what we call partial pressures of gases, as well as influenced by the solubility or the ease of the gas to dissolve within liquids, that is, the liquid within cells, as well as within the plasma, etc. So we're going to talk about each of these concepts. Partial pressure of gas. What we mean by that is that a mixture of gas, such as the environment, is made up of various gases, of course, and all of those gases together create a total pressure. So let's take a look at the atmosphere. Talked about atmospheric pressure equaling 760 millimeters of mercury. Well, the atmosphere is made of approximately 20% oxygen and approximately 80% nitrogen. So at 760 millimeters of mercury, 20% of that pressure is due to oxygen and 80% of that pressure is due to nitrogen. So for each of these gases, they exert a partial pressure, which is their part of the total pressure. So the partial pressure depends upon the fractional concentration of the gas. The total pressure of the gas mixture equals the percentage of that gas times the total pressure. So for oxygen, we have 20% of 760. So that would be the partial pressure for oxygen. So it is the proportion of the pressure of the entire gas mixture that is due to the presence of the individual gas. As I said, atmospheric air is approximately 80% nitrogen, approximately 20% oxygen. Different books round it differently. This particular book we're using rounds down to 79% nitrogen, 21% oxygen. There are trace amounts of carbon dioxide, helium, argon, and other gases, but these are so small that we ignore them because they're all less than 1%. And depending upon the amount of humidity, the amount of water in the atmosphere can be a consideration. If you've ever tried, even not exercising, just getting up and around and moving in a very, very humid environment, you know that the air actually feels heavier and thicker. Well, that's because of the fact that there's a fair amount of water in fairly humid air. And we'll talk a little bit more about that later. So atmospheric air said that the total gas pressure is 760 millimeters of mercury, but that is largely due to nitrogen and oxygen. So for nitrogen, we have the percent of nitrogen times the total gas pressure, giving us about 600 millimeters of mercury for the partial pressure for nitrogen. For oxygen, its partial pressure is about 160 millimeters of mercury. Atmospheric air is only about 0.03% carbon dioxide. So we end up with less than 1 millimeter mercury of pressure due to carbon dioxide, and for that reason, it is generally considered to be zero. But now this is atmospheric air, and assuming fairly dry atmospheric air. As I said, water can be a factor. So let's take a look at what happens with air that you breathe in. As we've already said in the previous lecture, that the air that actually is inspired, by the time it reaches the alveoli, has 100% humidity because it's fully saturated with water. Water vapor is a gas, and it has a certain partial pressure. And at body temperature, its partial pressure is about 47 millimeters of mercury. So rather than the partial pressures that we saw on the previous slide being relevant to the gas mixture in the alveoli, what we see is that we have to take into account the fact that this 47 millimeters of mercury of pressure is, because it's water vapor, is displacing both oxygen and nitrogen and the inspired gas mixture, so that what you end up with is the inspired partial pressure for nitrogen is rather than 600, it's 563. And for oxygen, rather than being 150 or 160 range, 160 is 149. And that's because we, again, have to account for this partial pressure of water in the inspired mixture. So we actually are inspiring even less oxygen in terms of partial pressure than what is available in the atmosphere because of the addition of this water vapor pressure. Now, as I mentioned before, factors that affect diffusion of gases. One of them is partial pressure, the other is solubility. So gas molecules can exist in a gas form, which of course, as we inspire air from the atmosphere, is in a gas form, or become dissolved in liquid. And if you think about what happens in the respiratory membrane, you have gas in the alveoli having to get through the membrane before it can get into the plasma. And in fact, before it even goes to a red blood cell and ultimately hemoglobin. So the gas is going to have to dissolve. It's going to have to dissolve in the respiratory membrane. That is, oxygen is going to have to dissolve in the respiratory epithelium, the vascular endothelium, and be dissolved in the plasma. So we're going to have gas dissolving in liquids in order to be exchanged. The ability of the gas to dissolve depends on the properties of the gas and the properties of the liquid. Both vaporized, that is, gas form, and dissolved gases exert partial pressures. And the partial pressure of the gas affects the amount of gas that goes into solution. So the higher the partial pressure, the more it dissolves. Because it is the pressure that is pushing that gas to become dissolved. Think about when you open a bottle of pop, or beer for that matter, if you're over age, hopefully, that as soon as you change the pressure in that bottle, that the gas that had been dissolved in the liquid now comes out. Because what you've done there, when you take the cap off, you've reduced the pressure, which means you reduce the amount that will dissolve so that the gas escapes. So the partial pressure of a gas affects the amount of the gas that goes into solution. The partial pressures of vaporized and dissolved gases will be equal at an equilibrium point. So let's take a look at solubility of the pertinent gases here. Here we're showing oxygen, here we're showing CO2. Oxygen, you will have much less oxygen that gets physically dissolved in the cellular fluids, extracellular fluids, etc., than in CO2. Because CO2 is 20-fold or 20 times more soluble than oxygen. So CO2 will, because it will dissolve more readily, does not need as much of a partial pressure to cause it to be exchanged. And in fact, we'll see that that is the case. So gases diffuse down their pressure gradient. They move from high pressure to low pressure. In a gas mixture, gases diffuse down their partial pressure gradient. Same thing, it's still a pressure gradient, but of course, the fact that there's more than one gas means each one has their own partial pressure. But it still moves from high partial pressure to low partial pressure. A particular gas diffuses down its own partial pressure gradient, and the presence of other gases is irrelevant. Again, the details in this diagram are a bit hard to see on the slide, so I encourage you to look at the appropriate figure here in your textbook as you follow along. But here we have the right heart, the left heart. The right heart, of course, is most important in this case because it's sending blood that came back from the tissues into the lung. So what we actually have here is a low partial pressure of oxygen. And the partial pressure of oxygen is about 40 millimeters of mercury. Now, on the rest of these, I'm not actually going to be referring to millimeters of mercury because it's the same unit for all of them. But the partial pressure for oxygen is 40. The partial pressure for CO2 is about 45 to 46. Different books, round it one way or another. So, of course, we have this poorly oxygenated blood coming into the pulmonary circulation. And, of course, we have oxygen coming in and CO2 leaving the alveoli, so that the oxygen partial pressure goes up. And it goes up to about 100. And the CO2 partial pressure drops down. And it goes from about 45 down to about 5. I'm sorry, down to about 40. So as the blood is leaving, we have the partial pressure of oxygen is about 100. For CO2, it's about 40. And that is because the blood in the pulmonary capillaries is equilibrating with the gas mixture, or I should say the gas in the blood is equilibrating with the gas in the alveoli. Then the blood's coming back to the heart. There's a certain amount of oxygen that's taken out by tissues in the airway as the blood is leaving the heart, going to systemic circulation. There's also a certain amount of oxygen taken out for the coronary circulation. So there's a small reduction. We have the oxygen dropping from about 100 millimeters of mercury down to about 95 or so. Some books talk about this decrease, some don't. But basically, there is a minimal loss. Then as this blood is going down through the arteries, of course, this is maintaining the same levels, about 100 for oxygen, about 40 for CO2. But then it encounters, and this is where the internal respiration comes in that we talked about on the first slide of the last handout. We, of course, have metabolically active tissue, which is consuming oxygen and producing CO2. So whereas the blood gas of the mixture coming in was 100 for oxygen and 40 for CO2, it very quickly drops down to about 40 for oxygen and about 45 or 46 for CO2, because we're consuming a great deal of oxygen and we are producing a fair amount of CO2. And these values stay at about the same level without any fluctuation as the blood accumulates back into the great veins coming back into the right heart. So the mixed venous, what we call the mixed venous blood gases, are the same as the blood gas of the pulmonary artery, because of course there is no additional exchange going on between the large veins and the right ventricle and the pulmonary artery. Now we have to look at the rate of diffusion, because of course each breath lasts a certain amount of time, as well as there's a certain amount of time that the blood travels through the pulmonary capillaries due to the cardiac cycle. Fortunately, the diffusion of gases between the alveolar gas and the dissolved gas in the blood is very, very rapid, because we have this very small diffusion barrier and a very large surface area. Remember, we have 0.2 microns in thickness and something about the size of a tennis court. So what happens is, as the blood's coming in, this is the partial pressure for oxygen, about 40, within about a third of the distance, because this is showing the length of the capillary as a percent of total. So about a third of the distance, that blood is already equilibrated with the alveolar CO2. Now, in terms of timing, this is about 1/4 of a second. So it occurs very very rapidly. And for CO2, again, the exchange is pretty much maximal by the time that blood is only gone about a third of the way through the pulmonary capillary. And again, this is about 1/4 of a second. So gas exchange and respiring tissue. What we mean by this is metabolically active tissue. This is internal respiration we're referring to here with this term respiring tissue. So the gases are going to diffuse down their partial pressure gradient. Of course, the partial pressure is higher in the blood than it is in the tissue. So within the cells, oxygen is very low, of course, because cells are metabolically active. So the oxygen partial pressure is probably about 40 millimeters of mercury, or even less, depending upon how metabolically active the tissue is. Within the arteries, arterioles, capillaries, at least at the arteriole end, the partial pressure is about 100. So oxygen diffuses from this high pressure, an area of high pressure, to an area of low pressure. So it diffuses from the blood into the cells. And then, of course, as the blood leaves the capillary bed, it is now depleted of oxygen. It is going to have a value that is going to be equivalent to whatever it was within the cells because, of course, of the equilibrium of exchange. Similarly for CO2, cells that are, all cells are metabolically active. Some are more so than others. So we're going to have 45, 46 millimeters of mercury partial pressure of CO2 within the cells. Greater metabolic activity, of course, means that this value will be even higher. Within the systemic arteries, arterioles, the arteriolar end of the capillaries, of course, we have a lower partial pressure for CO2. So the CO2 will move down its partial pressure gradient, diffusing from the cells into the blood. And the blood leaving the capillaries is, of course, going to have equilibrated with the CO2 within the tissue. Now, in physiology, we talk about mixed venous blood, and what we mean by that is blood leaving all these different capillary beds is going to ultimately get mixed together in the large veins, so that it would not be possible to measure the venous blood gas and get an actual estimate that's very accurate of what's going on in any given vascular bed when we take a blood sample out of a vein. So that's why we call it mixed venous blood, because the blood, by the time it gets into a vein that's large enough to insert a needle into it, has a mixture of blood coming from tissues with varying degrees of metabolic activity and therefore varying consumption of oxygen and production of CO2. And of course, greater metabolic rate of metabolism means greater exchange. So the partial pressures for these two gases are going to be different in different veins. There's going to be variation. But by the time all the systemic blood returns to the right atrium and is pumped out of the right ventricle into the pulmonary artery, it is a mixture of the blood from the various parts of the body. And even though different capillary beds may have different partial pressures for both oxygen and CO2, because we have this mixture, also called a venous admixture, getting to the lungs, it generally is going to have this fairly invariant partial pressure profile. So what are the determinants of these partial pressures in the alveoli? Well, first of all, the partial pressure of oxygen and CO2 of the inspired air. Again, if we go to a higher atmosphere, let's say Denver, there are fewer gas molecules in the atmosphere because it's higher up in the atmosphere. Gravity is, of course, exerting a lower amount of pull on the gas molecules. So even though the percent of oxygen is the same, the total amount is lower. The total pressure, atmospheric pressure, is lower. So 20% of a smaller amount is, of course, going to be a smaller amount. So the partial pressure of oxygen is going to be lower because the total pressure of the gas, of the atmospheric gas in Denver or other high altitude places is also lower. Other factors that will affect alveolar partial pressure is minute alveolar ventilation. If somebody increases minute alveolar ventilation, of course, that will also increase alveolar ventilation ultimately, and that will, of course, increase oxygen and decrease CO2. And conversely, if you decrease ventilation, you're going to decrease the partial pressure of oxygen and increase the partial pressure of CO2. Generally, the rates at which the respiring tissue use oxygen and produce CO2 are going to be fairly constant. But of course, those rates can change depending upon the metabolic activity of the tissue. And of course, that is going to increase or decrease the amount of oxygen consumed and the amount of CO2 produced. The most critical is the rate of alveolar ventilation relative to the oxygen use and carbon dioxide production. So It is the ventilation rate itself that is generally the most critical. Now, with this, we have to match ventilation to the need. So there's several terms that are used here. Hyperpnea is when there's increased ventilation due to increased demand. And this is going to mean that there are going to be minimal changes in arterial partial pressure for oxygen and CO2 because the increased ventilation is going to match the demand, which means we're bringing in more oxygen when it's being used and we're blowing off more CO2 when it's being produced. Hypoventilation, ventilation does not meet demands. So arterial partial pressure of oxygen will be lower than normal, and arterial partial pressure of CO2 will be higher than normal because we are not ventilating adequately to meet the metabolic demands. Hyperventilation is the opposite. Ventilation exceeds demands. So in this case, arterial partial pressure of oxygen will be generally above normal, and arterial partial pressure of CO2 will be below normal. So we've been talking about exchange. Now let's talk about how we actually transport the gases in the blood, because obviously exchange can't take place unless we have transport. So I've already mentioned that oxygen is not very soluble in plasma. It only is about 1/20th as soluble as CO2 is. So only about 3 milliliters of oxygen will be dissolved in 200 milliliters of arterial blood. So only about 1.5% of our oxygen can actually be physically dissolved. The other 197 mils have to be transported by hemoglobin. So that would mean, of course, that 98.5% of our oxygen is transported by hemoglobin. So let's look at how oxygen binds to hemoglobin. Hemoglobin can bind to oxygen to produce what's called oxyhemoglobin. Hemoglobin that is not bound is called deoxyhemoglobin. So as blood is coming in this case you have a low partial pressure of oxygen in the blood coming into the pulmonary capillaries, encountering a high partial pressure of oxygen in the alveolar space, we have equilibration. And what's happening is that the oxygen is moving from the alveolar gas mixture. It's, of course, physically dissolving at all of these steps here. The alveolar epithelium, interstitial space, capillary endothelium, stays physically dissolved in the plasma, physically dissolves going through the membrane of the red blood cell, stays physically dissolved in the intracellular fluid, but eventually will meet the hemoglobin molecule and form oxyhemoglobin. Now, hemoglobin has 4 binding sites for oxygen, so that it means that it can be saturated. So the binding of oxygen to hemoglobin follows what's called the law of mass action, meaning that more oxygen means that there's going to be greater binding to hemoglobin. But of course, up to a maximal level because it can saturate. But it's a nonlinear relationship because these 4 binding sites that you have, when the first one is bound to oxygen, it alters the affinity of the other 3 for oxygen. And when the second one binds to oxygen, it further alters the other 2 binding sites. And this is what we call positive cooperativity. So as each one binds oxygen, it enhances the binding of subsequent hemoglobin molecules to oxygen. So the saturation of hemoglobin is a measure, first of all, of how much oxygen is being bound to hemoglobin. 100% saturation means all 4 binding sites in the hemoglobin molecule have hemoglobin bound to them. Now, the only way you're going to get 100% saturation in all molecules of hemoglobin in an individual's body is to be breathing a partial pressure of oxygen of 760 millimeters of mercury, because you're going to need that much partial pressure to move a sufficient number of oxygen molecules to all of the binding sites. So generally, rather than having 100% saturation, normal saturation, somewhere between 97 and 98%. which is still pretty saturated. So let's take a look at these binding sites. In arterial blood, hemoglobin is about 98.5% saturated. And what we have here is we have all of these hemoglobin molecules with all 4 binding sites saturated. It's easier to show the one that's not. But here is a molecule of hemoglobin that only has 3 of the 4 binding sites bound to oxygen. In venous blood, hemoglobin is only about 75% saturated, which is a remarkable thing if you think about it. The blood coming back to the heart, unless a person is having respiratory problems or engage in extremely vigorous exercise, will the venous blood be less than 75% saturated. And even in that case, disease is more likely to have an effect than exercise. So in this case, what we actually have is virtually every one of these hemoglobin molecules within this red blood cell is 75% bound. So there's not really that much of a change between what we have in the arterial blood and here, because still most of these molecules are nearly saturated. So the hemoglobin really is an amazing molecule in terms of its ability to carry vast amounts of oxygen. But with this, we have to talk about the concept of oxygen carrying capacity of the blood, because the saturation of hemoglobin is only part of the story in terms of how much oxygen the blood is carrying. So when hemoglobin is 100% saturated, there is a gram of hemoglobin carrying 1.3 milliliters of oxygen. Normal hemoglobin levels are about 12 to 17 grams per deciliter of blood, meaning that the oxygen carrying capacity of hemoglobin in the blood is about 200 milliliters of oxygen per liter of blood. So each liter of blood will carry about 250 milliliters of oxygen that can become gas and be delivered to the tissue. So let's take a look at what's called the oxyhemoglobin or oxygen dissociation curve. So what we're looking at here is the saturation of hemoglobin. With 100% here, 0% down here, etc. And this is partial pressure of oxygen. So the systemic veins, we said the partial pressure of oxygen is that the saturation of hemoglobin by oxygen is about 75%. So that's what we're showing here. And that is, of course, a partial pressure of about 40 millimeters of mercury for oxygen in the systemic veins. And the systemic arteries, where the partial pressure for oxygen is about 100, we have something close to, but not quite 100%. Remember, this is about 98.5% saturated. So think about this. We're moving from the systemic veins to the systemic arteries. So as the blood is circulating through the system, we're having fairly small changes in the saturation of hemoglobin. It's still maintaining at least 75% or greater saturation. What is it going to take to have hemoglobin become less saturated? Well, if you increase metabolic activity substantially and decrease the partial pressure in the tissue, let's say from 40 down to 20, so we're extracting an enormous amount of oxygen, hemoglobin is going to go down to maybe about 40% saturated, which is still quite astonishing when you think about it, the fact that it's 40% of its binding sites are still occupied with hemoglobin. So what it's actually taking is fairly, and if you look at this part of the curve versus these other parts over here, that as oxygen level goes down, hemoglobin loses its oxygen more readily, because this is the driving pressure causing the movement of oxygen here. As hemoglobin becomes more and more saturated, it takes more and more pressure to cause its saturation. So here, 20 millimeters of mercury in pressure made a difference of, let's say, from, 25 or 30% up to about 75%. Whereas 20%, again, another 20 milliliters, I should say, or 20 millimeters of mercury here makes a much smaller difference in the saturation. So this is an indication of the interaction between the binding affinity for hemoglobin and the partial pressure of oxygen, and reflects also this cooperativity of binding that we talked about. It also means that as tissue becomes more metabolically active and oxygen partial pressure declines, that the hemoglobin gives up its oxygen far more readily, which of course you would want it to do, as a way of helping to make sure that the tissue maintains an adequate supply of oxygen. There are factors that can change this curve. So this is the same curve here on this slide as we're showing here, but this middle curve was the one we were seeing on the previous slide. In this case, we're shifting it to the right, which means a decreased affinity of hemoglobin for oxygen. So there's less loading of oxygen, that is that the hemoglobin takes on a smaller load of oxygen, as well as less unloading. Well, why do we say it's decreased affinity? Well, as the curve shifts to the right, a larger pressure difference is necessary to produce the same level of saturation. If it shifts to the left, it means there's an increased affinity of hemoglobin for oxygen, that more oxygen will be bound or loaded onto the hemoglobin and less will be unloaded. So let's look at some of the factors that alter that. Higher temperature. As tissue is more metabolically active, that temperature increases, it's going to shift the curve to the right. So it's going to decrease the affinity of hemoglobin for oxygen, meaning more oxygen is being unloaded in the tissue, which makes sense. If you have greater metabolic activity, tissue that's more active, it needs more oxygen. So you want more oxygen to be delivered. You want more oxygen to be delivered to the tissue. If the opposite were to happen, that you have the tissue being less metabolically active, temperature is likely to be a little bit lower, and you would have less delivery of oxygen to the tissue, which makes sense. The tissue is less metabolically active. It doesn't need as much oxygen. pH effects. This is also referred to as the Bohr effect. That lowering the pH increases the unloading or the delivery of oxygen. Well, pH goes down when metabolism goes up. So again, it makes sense. Active tissue produces a more acidic pH. So we're having a shift to the right, causing a shift to the right in the saturation curve so that more oxygen is unloaded to the tissues. Similarly for CO2, it's also called the carbamino effect, that as CO2 levels increase, it will also reduce the affinity of hemoglobin for oxygen. In addition, CO2 can actually bind to hemoglobin, producing what we call carbamino compounds. So carbon dioxide can react with hemoglobin to form carbamino hemoglobin. And depending upon the number of the number of CO2 molecules that are bound to a molecule of hemoglobin, as well as the amount of hydrogen ions that combine, we have actually a variety of types of carbamino hemoglobin. But carbamino hemoglobin has a lower affinity for oxygen than does hemoglobin itself. And of course, increased metabolic activity increases the amount of oxygen being produced, which is going to, because it lowers the affinity of hemoglobin for oxygen, is going to increase the oxygen unloading in the active tissue. So all of these factors we've talked about in the last few slides are chemical means of increasing the oxygen delivery to the tissue that needs it most. One last factor here is 2,3-DPG, which is 2,3-diphosphoglycerate. It is produced in red blood cells under conditions of low oxygen, such as anemia or high altitude. And its synthesis is inhibited by oxyhemoglobin. 2,3-DPG decreases the affinity of hemoglobin for oxygen and therefore enhances oxygen unloading. So this is a molecule that is designed to help maintain the homeostasis of oxygen delivery based upon oxygen need. Carbon monoxide can be a factor. It's not normally a factor, but of course a person could be exposed to elevated levels of carbon monoxide either in the way of air pollution or unfortunate incidences that can occur in a car where somebody's exposed to a fair amount of carbon monoxide. Hemoglobin has a much greater affinity for carbon monoxide than for oxygen, and this is the chemical equation, or chemical symbol, I should say, for carbon monoxide. It is a carbon with one mono oxygen. And prevents oxygen from binding to hemoglobin, which is one reason that carbon monoxide poisoning is so dangerous. And the affinity of hemoglobin for carbon monoxide is extremely high compared to that for oxygen. So it prevents oxygen binding to hemoglobin for a very long time. Take a look at how carbon dioxide is transported in the blood. Even though carbon dioxide is more soluble in the plasma than oxygen, as I said, 20 times more, only 5 to 6% is transported in the plasma, which of course is more than we saw for oxygen. Remember, oxygen was about 1.5%. But carbon dioxide can bind to hemoglobin to form carbaminohemoglobin, as we said before, and in fact, about 5 to 8% of the total amount of carbon monoxide or carbon dioxide that's being transported is being transported by hemoglobin. So we had 5 to 6% dissolved, 5 to 8% bound to hemoglobin. The remaining 86 to 90% is transported, dissolved in the plasma as the bicarbonate ion, which is HCO3 with a negative charge. It is an anion. So carbon dioxide can be converted to bicarbonate ion by the erythrocytes, and then is transported in the plasma that way. Carbonic anhydrase is an important enzyme. It's the enzyme that converts carbon dioxide and water into carbonic acid. So what's actually happening in the erythrocytes when they're converting carbon dioxide into bicarbonate ion is shown in this chemical equation. Carbon dioxide and water will form carbonic acid. And the enzyme carbonic anhydrase, and it does, as all enzymes do, is that it hastens the reaction. The carbonic acid will break down into protons or hydrogen ion, and of course all acids by definition produce increased hydrogen ion. That's what the pH measures, is the proportion of hydrogen ion, and bicarbonate. So we have an acid here and a base. According to the law of mass action, an increase in CO2 is going to cause an increase in bicarbonate and hydrogen ions. So CO2 goes up, it pushes the reaction this way, causing more bicarbonate as well as more hydrogen ions. And if you think about it this way, CO2, this molecule is embedded here. You have CO3, which contains a CO2. So I like to think about it that way. It helps me to think about how bicarbonate is carrying CO2. As we'll see when we get into the renal system, we're talking about acid-base balance, that this is a very important equation, because CO2 also is going to increase the acidity or decrease the pH of the blood. So let's look at CO2 exchange. So we have CO2 being produced in the tissue, blood coming in. Of course, the partial pressure of CO2 in the arterial blood is about 40. As it's leaving, it's 45, 46 millimeters of mercury, because we have the tissue producing lots of CO2. The CO2 is diffusing down its partial pressure gradient, and it is going to, the equation that we see here, the CO2 plus water forming carbonic acid, which dissociates into bicarb and hydrogen ion, and then the bicarbonate is going to diffuse out of the cell. This chloride shown here, there's actually an exchange of chloride for bicarbonate, because we're losing a negatively charged ion here. In order to maintain electrical neutrality, we have to take on another negatively charged ion in exchange. So there is a bicarbonate and chloride exchange going on here. This is what's occurring in the lungs. So get back to the tissue, of course, we have our bicarbonate that's been circulating around in the plasma. The bicarbonate is now going to reverse direction going into the erythrocyte, and it is going to bind to or interact with a proton, a hydrogen ion, that is coming off a carbamino compound here, forming carbonic acid. Carbonic anhydrase is going to allow that, of course, to dissociate into water and CO2, and then the water is moving down, the CO2 is moving down its pressure gradient into the alveoli, and all of this, of course, is occurring in the lungs. So we saw before that CO2 can affect oxygen binding by hemoglobin, and therefore oxygen transport. Partial pressure of O2 can affect CO2 transport as well. So the total blood CO2 content for a given partial pressure of CO2, if oxygen partial pressure moves down, you actually transport more CO2. So just as CO2 affects hemoglobin's affinity for oxygen, oxygen affects hemoglobin's affinity for CO2. Now, how is all of this regulated? Well, in part through the central nervous system, what we call the chemoreceptors. And when we talk about the chemoreceptors in this regard, the two chemicals that we're interested in are oxygen and CO2. So in the arterial blood, as the partial pressure of oxygen decreases, it stimulates what's called the peripheral chemoreceptors, which are out there in the aortic artery. These are going to detect this change and respond by stimulating brainstem respiratory control centers, which are going to increase ventilation by increasing the activation of respiratory motor neurons going to the inspiratory muscles. Similarly, an increase in CO2 will stimulate peripheral chemoreceptors, and because of its increase in the increase of hydrogen ion will activate central chemoreceptors. Now, these are on the brainstem, which is why they're called central. So the CO2 increase, of course, is affecting hydrogen ion concentration, or pH, everywhere, in the blood as well as in the cerebrospinal fluid. Cerebrospinal fluid is a filtrate of arterial blood. So it's going to take a certain amount of time for the cerebrospinal fluid partial pressure of CO2 to increase, but of course it will, because it's going to be moving down its pressure gradient. This is going to acidify the cerebrospinal fluid, which will stimulate the central chemoreceptors, and these will also increase ventilation. So these chemoreceptor reflexes are a way of maintaining homeostasis for both oxygen and for CO2. The peripheral chemoreceptors are responsive primarily to oxygen. This diagram shows them responding to CO2, and frankly, there's a fair amount of debate going on about that. But most sources agree that CO2 definitely stimulates the peripheral chemoreceptors. Oxygen stimulates peripheral chemoreceptors. CO2 is questionable. It may or may not, but CO2 does stimulate the peripheral chemoreceptors. Now, in order to have exchange and transport happen efficiently, we have to match ventilation to blood flow, or perfusion. So ventilation is the rate of airflow, and perfusion is the rate of blood flow through the lungs. So locally, that is, for a given capillary and alveolus, we have to have local ventilation and perfusion regulated in order to match each other. And we refer to this as the ventilation-perfusion ratio. And since the abbreviation for ventilation of the alveolus is V subscript capital A, and for cardiac output, which of course is our blood flow, the abbreviation is Q. This is also referred to as the VQ ratio, which is just a shorthand for ventilation-perfusion ratio. So there is carefully regulated matching of the amount of ventilation in the alveolus and the amount of blood flow, allowing gas to exchange there. If we have reduced or blocked ventilation, this is going to mean that the blood entering the lung is going to leave the lung, or at least this capillary, unchanged. And that one way of responding to that is that these blood vessels that are encountering poorly ventilated alveoli will actually constrict, because as oxygen level stays low within the pulmonary capillaries, if oxygen level is low, this causes constriction of the capillary. So by constricting, of course, it's increasing the resistance for blood flow, which means less blood will flow through here to divert more of the blood to well-ventilated alveoli. If you have the opposite problem, if you have some sort of restriction of blood flow, you have alveolar ventilation going on that is not participating in exchange because there is no blood here flowing through to participate in exchange. And as CO2 level increases, as well as oxygen level decreasing or staying low in this blood, you're going to have compensatory changes occurring here in the airways that are going to try to match this ventilation to the perfusion. So let's take a look at how these are matched. So if we have here alveoli and pulmonary interstitial fluids, of course the gas is moving from the alveolar gas into the interstitial fluid. As CO2 increases, this is going to cause an increase in the contractile activity of the smooth muscle in the bronchioles, causing a bronchodilation. This is going to decrease the resistance for airflow, which will increase the amount of air getting into the alveoli. Now let's go back to this previous diagram. Here is showing a complete blockage, which is an extreme case. Suppose rather than an extreme complete blockage, you have a reduction in blood flow here. That is consistent with what we're talking about here, that CO2 would increase, oxygen would decrease, and it would cause these responses that we just talked about in the bronchioles, that it will cause a relaxation of the smooth muscle in the airways, causing bronchodilation, which is going to decrease the resistance to airflow, increasing ventilation, as a way of trying to get more gas there to participate in maximal exchange with that amount of blood. Basically, it's a way of trying to restore the normal partial pressure of CO2 and O2 in that particular space around that alveolus. Then the effect on the arterioles. Both of these, again, increasing CO2, decreasing oxygen, is going to increase the contractile activity of the smooth muscle, causing vasoconstriction, which is going to increase the resistance to blood flow, decreasing perfusion. So again, we have here a series of events going on that is trying to match ventilation with perfusion as a way of maintaining maximum exchange between the two gas compartments. I have to talk about acid-base balance. Again, I mentioned we'll talk about this in more detail in the chapter on renal physiology. But we need to introduce the concept here. So the pH of the blood, this is relating to the acidity. The normal pH of blood is about 7.4. The normal range is about 7.30 to 7.42. The pH is a measure of how many hydrogen ions are in the blood. So there are respiratory and renal systems that regulate pH. Of course, we can't understand the renal systems until we get there, so for this point we'll skim over that. The small changes in pH have large physiological effects. They alter protein activity drastically. This is one reason pH range is held in such a narrow homeostatic window, is because the protein activity, particularly enzymes, are highly dependent upon a very narrow range of pH values. So, of course, enzymes are going to not function very well if the pH range gets outside that normal value. If the pH drops below 7.35, it's called acidosis, which can cause depression of the central nervous system. It can cause many other problems as well, but this is something that we can see a person becomes very agitated. If pH increases above 7.45, it's called alkalosis because the blood has become very alkaline, or another term is very basic. And this can cause CNS overexcitation. And I'm sorry, I misspoke before. This would be agitation. In this case, CNS depression. A person might become an extremely severe problem, could become comatose. But before that, of course, they could become lethargic, sleepy, that sort of thing, fairly unresponsive to stimulation. So let's take a look at how the respiratory system works in acid-base balance. Well, hemoglobin functions as a buffer. That is, a buffer is something that binds these hydrogen ions. So hemoglobin, especially deoxyhemoglobin, has a very high affinity for hydrogen ion. So again, where is the deoxyhemoglobin most likely to occur? Well, in metabolically active tissues. So the hemoglobin's given up its oxygen to metabolically active tissue. There's, of course, a generous supply of hydrogen ions available in the metabolically active tissue, so that the hemoglobin will then bind the hydrogen ion. This is the beginning of the carbamino compounds we talked about before. Bicarbonate ions also can act as a buffer, because here we have our hydrogen ions that we're referring to in terms of the blood acidity, and hydrogen ions will bind to bicarbonate. In this case, hydrogen is an acid, bicarbonate's acting as a base. An acid and a base together will form an acidic substance, in this case carbonic acid, which will dissociate into CO2 and water. Now, this is the really important thing in terms of respiratory system and acid-base balance. This CO2 molecule is functionally equivalent to this hydrogen ion. And for this reason, CO2 is quite often called a volatile acid. Of course, from a chemist standpoint, it's not an acid at all. But from a physiologic standpoint, as CO2 is eliminated from the body, we've eliminated a hydrogen ion. So it acts as though it's an acid and volatile, meaning that it can be blown off. So the respiratory system regulates pH by regulating CO2 levels. Let's take a look at acid-base balance a little bit more. This is what's called the Henderson-Hasselbalch equation. The pH of the blood equals 6.1 plus the log of this ratio between the concentration, plasma concentration of bicarbonate versus the plasma concentration for CO2. So to maintain the normal pH of about 7.4, this ratio right here, has to have a value of 20 to 1. Well, the respiratory system regulates CO2 concentration, and as we'll see when we get into renal physiology, the kidneys regulate primarily bicarbonate concentration by both reclaiming bicarbonate that gets filtered out of the plasma as well as synthesizing new bicarbonate. So by regulating these two components of this ratio, both kidneys and lungs work together to regulate pH. Let's look at disturbances of acid-base balance. Respiratory acidosis, that is when pH is below normal, and it's due to the respiratory system, it is because there is an increased CO2 concentration. It makes sense given what we said in the previous slide, 2 slides back, that if the CO2 molecule is functionally equivalent to a hydrogen ion, then increasing CO2 is going to cause acidosis, or in that case, a decrease in pH, making the blood more acidic. And this would be called respiratory acidosis because it is due to a change in CO2. Respiratory alkalosis, which is when pH increases above normal, is due to decreased CO2 because the respiratory system is not blowing off as